Okay, I gotta sorry about this. I've got to get rid of this old recording here. Now we got the new one going. All right, now let's do a problem. Let's do a problem. And what I'm going to do is I'm going to show you the problem I'm working on in the book here, and we're going to do this amusement park ride. In the amusement park, Magic Mountain Superman, powerful magnets accelerate a car and its riders from rest to 45 meters per second. That's almost 100 miles an hour. In a time of 7 seconds. The combined mass of the car and riders is 5.5 times 10 to the third kilograms. Find the average net force. Now this is the average net force because with magnets it gets stronger. Force actually gets stronger the closer to the magnet you get. But anyway, find the average net force exerted on the car and the riders by the magnets. Okay, this is a classic. The net force mass times acceleration. So we've got this car. Whoops, that's a little bit too much of my fuzzy hand. All right, there we go. Now then, sorry. Now we got this. So we've got this roller coaster type car, I guess, and it's being accelerated. It's got a force going this way. It's got a net force going this way. Now we're the net force. All right, and later on we'll look at all the other forces. There's gravity pulling it down and that pulling it up, right? But we don't know what this net force is. We do know that the mass of this car is, what did they say? 5 point something? 5.5 times 10 to the third kilograms. All right. And we know that the time it took was 7 seconds. The initial velocity is 0, and the final velocity is 45 meters per second, which is very, very close to 100 miles an hour. It is. All right. Wow, that's really, really fast. You know, I'm sure if it's Disney, it's very safe. But anyway, hey, notice we have a chapter 2 problem because I know that the net force acting on this, which is this guy, all the net forces is equal to, and it's a vector, is equal to the mass times the acceleration. Can I get the acceleration from this? From this information? What is the definition of the acceleration? Final velocity minus the initial velocity divided by time. That's the average acceleration. Can we do that? I wish they'd have said it's 49 meters per second or 42 meters per second. Then we get a nice acceleration of 6 or 7. But as it is, we don't have that luxury. So we've got to do this. We've got to take 45 minus 0 divided by 7. And that's 6.42 meters per second squared. Now, here's the important part. This acceleration is in the same direction as the force. That's huge. The net forces is in the same direction as the acceleration. You might think, well, that's obvious. No, it's not. And as we get into more complicated problems, not complicated, just more moving parts, you'll see that it's not so much. All right, so sum of the forces, then, which is what we don't know, is equal to 5.5 times 10 to the third kilograms times 6.42 meters per second squared. Notice I've got kilograms, meters per second squared. That's my units. That's my newtons. So I'll take 5.5 second e to the third times my answer from before. Bang. 3.54. I'm going to go 3 sig figs. 3.54 times 10 to the fourth. Units, please. Newtons. You got it. All right. Doesn't seem that hard, right? Does not seem that hard. Let's look at let's look at another problem. I know this one might be this, but let's look at one in two directions. All right. So here we go. Let me smoosh this down. It's in your book. These are all taken from your text. All right. So we're going to look at problem 11 here. And it says only two forces act on an object which has a mass of 3 kilograms. Okay, I got 40 newtons acting this way, and I got 60 newtons acting at a 45-degree angle that way. Find the magnitude and direction of the acceleration of the object. All right, and I might add a wrinkle to that. Okay, I might just add, you know me. So this is September 13, page 1. Sorry, wasting your time. All right, so got a block. And the only forces acting on it, 40 newtons this way, 60 newtons this way, at a 45-degree angle. All right, first of all, let's start with the free body diagram. FBD, big friendly giant. That just killed me. The BFG. I was like, are you kidding me? People are really... I cracked up every time I saw it. You know, I'd go to the movies and they'd have this thing for the big friendly giant. And I'd be like, what? Are you kidding me? BFG. It was a big freaking guy. Sorry. I'm terrible. I know it. I know. I'm evil. But anyway, so the mass of the object's 3 kilograms. So here's the free body diagram. Because we're assuming everything's coming, we're pulling everything from the center of mass. Okay. And then I'm going to add a wrinkle. I want to know what's its final velocity after 3 seconds. This is part 2. So again, you've got to do work from, so you got to know chapter 2 to be able to solve the second part of this. All right. So here's what we do. We break it down to its components. The sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. Sum of the forces in the y direction is equal to the mass times the sum of the forces times the acceleration in the y direction. Okay. Forces in the x direction are force 1 is equal to 40 newtons. Force 2 is equal to 60 newtons times the cosine of 45 degrees. This one, force 1, in the y direction is equal to 0. Force 2 in the y direction is equal to 60 newtons sine of 45 degrees. Those of you that are used to trig go, oh, well, they're going to be the same number. Yes, they are. All right? And so that's what we'll do to solve. That's how we'll solve this. And so we got to find 60 newtons. First of all, I want to get out of this scientific notation mode. All right? So I've got, what do we have? So the sum of the forces here in the x direction is equal to 40 plus 60 times the cosine of 45. These are all positive. So that's 82.4 newtons. And the sum of the forces in the y direction is equal to, 60 sine 45, which is 42.43. So the net force on this object is equal to 82.4 squared plus 42.4 squared. Okay, and take the square root of that whole thing. .92 newtons, 92.6 newtons, 0.7 newtons we'll go with. All right, so the acceleration on this object, since it's 3 kilograms, and it would be going in a direction like this. Something like that. Really? Yeah, so the direction of this thing is the inverse tangent of 42 over 82.4. So the inverse tangent of 42 divided by 82.4 is equal to 27 degrees. See, it's much smaller than that 45 that they're at because this force is a lot bigger than this one. So the sum of the forces in the y direction, or the sum of the forces total, is equal to 3 kilograms times the acceleration. So the overall acceleration is 92.7 divided by 3.0, 30.9 meters per second squared. So, I mean, those are pretty strong forces acting on something. They're not real strong, but look at that. That's a heck of an acceleration. So what's the final velocity after, what did I say, 3 seconds? Final velocity would equal v naught, which the initial velocity we're assuming is 0, plus 3 seconds times 30.9 meters per second squared. Notice I got seconds here. That cancels that, and I wind up with, what, 92.7? Oh, that's, well, yeah, it's going to be the same as the newtons because I did 3 seconds. That was just a fluke because it's 3 kilograms and it's 3 seconds. So, all right. That was a little long, but it was important. And then now we're going to look at Newton's third law.